Hi guys, this is Unit 13 from the HLAI course. It's about probability distributions. It starts off with a whole load of definitions, which is kind of formalizing some of the work which you've done before in probability. So it talks about probability distribution functions. It talks about cumulative distribution functions. We're talking about discrete cases and not continuous. That is to say, we have discrete outcomes, like, for example, the outcomes on a dice. We also talk about expected values of distributions here and whether or not games can be fair. Okay, so let's deal with this through an example. So let's actually deal with the example of a dice. So we could say that x, which is our variable in this case, one second, move that up a second. So x, which is could be the outcome on a dice. So could be the number that you get or the outcome on a fair six-sided dice. Okay, and so that's your uppercase x, and lowercase x would represent a particular outcome. So we can put this now into a table by saying, okay, what are our particular outcomes here? So let's just put x there, and then what's the probability that x is equal to x? So our outcomes could be, of course, 1, 2, 3, 4, 5, and 6. So the answers that we can get from rolling a dice. And the probability in this case is the same for all of them. Now, obviously, this is a simple example, but there may be cases where you have to do quite a bit of working out to find these probabilities in this line. And later on in another example, I'll show you that you can add extra lines in here to consider some of the outcomes that lead to the probabilities. Okay, so there you go. That's our normal probability distribution table here. And you can see that in their definition, they're talking about t, I'm talking about x, same really. They come up with f of t, which in our case we can call f of x, is equal to p, x is equal to x. So basically two ways of saying exactly the same thing. So in our case here, if you wanted to say, for example, f of 2, what's the chance of getting a 2? Well, the probability of that is going to be a sixth. So you can write a sixth there. Now, in terms of cumulative distribution functions, they just use slightly different notation. They say f of t, f of x, if you like. And so, for example, f of, I don't know, let's say 3 would be equal to the probability that x is less than or equal to 3. Okay, so in that case, that would be f of 1, lowercase f of 1, plus f of 2, plus f of 3, which is what it's talking about when it's coming up with this summation notation here. We'd be saying sum from n is equal to a, in this case, a is equal to 1. It's the minimum value that the domain of this domain, in this case, so it would be 1 in that case. So this one would be f of 1 plus f of 2 plus f of 3, which, of course, when we add these three probabilities together, we're going to get 3/6, or in other words, a half. So chances of getting up to and including a 3 on a single throw of a dice would be a half. Okay, so then we can also deal with expected values here as well. So let's just get rid of this. Just remember this at the moment. Pretty simple to remember. But then they talk about expected values. So e of x, e of this random variable, what's the expected outcome? Let's think about this in terms of the dice situation again. So what's the expected outcome when we have a fair dice? And that we can call mu. So that's mu if you want to pronounce it. So that's mu. So the expected outcome in this case is the summation of all of your x's times by p of x is equal to x. So in our table, we had x was equal to 1, 2, 3, and so on. And the probability, or if you like, f of x, so probability x is equal to x, was a sixth, and so on. Okay, and so on in this case. So what are we going to do? We're going to times all of our x's by our probabilities and then sum them all together. So in this case, we're going to say e of x equals 1 multiplied by a sixth plus 2 multiplied by a sixth plus, and so on, until you get to a sixth times by a sixth. Okay, now when you do that calculation, you end up getting 21 over 6, and 21 over 6 is equal to 3.5. In other words, the expected outcome when you roll a six-sided dice is 3.5. So obviously you can't get 3.5, but that is the answer to the expected value. You can leave it as a decimal answer there, but you can make some sense of that thinking, well, I don't know what we're going to get from 1 to 6. It could be a low number or it could be a high number. Our two middle numbers are 3 and 4, so I guess it averages out to 3.5 if we did this experiment lots of times. So if we only had one guess to make, we'd say 3 or 4 would be our expected value, but we go with 3.5. Okay, so 3.5 is the expected value in that case. Okay, so one final thing is in the notes. It says that if x is a discrete random variable that represents the gain of a player, and if e of x is equal to 0, then the game is fair. When they talk about gain, often you'll be presented with situations where you're given the payback from the game, the particular game that you're looking at. And that can be seen as a sort of revenue, if you like, but often there will be a cost to the game. So when we think of gain in this sense, it's a bit like thinking about profit. Okay, profit being your revenue, so what you're getting back, take away your costs. Okay, and we're going to look at an example next where this is the case. Okay. Hi guys, so this is a question from 13A. This is question 6. This is a scenario where 3 coins are being tossed and there are various outcomes to this game. This is also one of those questions which ends up talking about whether or not the game is fair or how do you make the game fair. Okay, so 3 coins are tossed and Marin wins $15 if he gets all 3 as heads, $5 if he gets 2 heads, $Y if he gets 1 head, and $2 if no heads occur at all. And it says that M is the discrete random variable representing Marin's winnings. Okay, so that's the winnings. So whereas before we might have had X as the number of heads or T as the number of heads, here we're talking about M representing the winnings instead. Now it's possible that you could make a chart up with X in and X, lowercase x, and the probability of X equaling to X, and then M, and probability of M equaling to M. I think I'm going to skip that though. I'm going to make it as quick as possible. So in this case, we could make a little chart up saying what's M. So M is 2, Y, 5, or 15. And then we've got the probability that M is equal to M there. And so there is an 1/8 chance of getting a 2, a 3/8 chance of getting a Y, 3/8 chance of getting a Y there, and an 1/8 chance of getting a 15. Now, likewise, we could have called these X. X could have been 0, 1, 2, or 3. We could have put in an extra row there if we wanted to. But I've gone straight to writing down M and the probability of getting that M. But of course, M relies on, for example, 3 heads. Now, often there's a bit of work that you need to do before you get these probabilities. It might be that sometimes you need to do sample space diagrams, for example, where there's some operator between, I don't know, 2 dice that have been thrown. In this case, you might wish to do a list of your outcomes, for example, or potentially a tree diagram with heads and tails and heads and tails and heads and tails. Now you can see that there would be 1 route out of a total possible of 8 routes there, 2 times 2 times 2, which would lead to 3 heads. But you could also list your outcomes if you wanted to. Like, for example, getting 2 heads would be heads, heads, tails, heads, tails, heads, and tails, heads, heads as well. So there's 3 out of a possible total of 8 routes through this massive tree diagram, which would give you the chance of getting 2 heads. Okay, so there's potentially quite a bit of working out to do to get these probabilities, and you could go with 0, 1, 2, and 3 there at the same time, and then put in m instead. Okay, so then the next part of the question says work out E of m. So find the expected value of m, which is fairly straightforward. Of course, you're going to do this times and all of these, and then these multiplied together and then summed up. If you do that, then you end up getting, so I just did it aside a moment ago, you end up getting 4 plus 3/8 y. 3/8 of y, and the others sum to 4 when you multiply them together. Okay, so for part B, it says find the value of y that makes the game fair if Marion pays $7 to play 1 game. Okay, now remember that for a game to be fair, then the total gain needs to be 0. Now, in this case, there's already a loss of $7 as soon as you go to play the game. So E of M is actually representing revenue, if you like. It's how much you're getting back. It's the total amount that you're taking from it. It's not profit. So profit would be gain, if you like. So in fact, what we could do is we could change all of these numbers here to say, well, if we wanted to take into account the $7 there that's being paid out, then actually this becomes -5, and this becomes y minus 7, and this becomes -2, and this becomes 8. All I'm doing is taking 7 off them. Now I could times this by this, these numbers on the top with these probabilities, add them together and equal them to 0. But I'm making way too much work of this, because actually what I can do is set my revenue equal to 7. I want to get back my expected revenue. Expected revenue needs to equal to 7. I want to get back my money overall in the long term, if you like. So all I need to do is set this equal, in this case, to 7, and that would give me a fair price. As I said, this is like talking about revenue rather than profit, and we really need to set the profit equal to 0 or the gain equal to 0, the expected gain equal to 0 to make this a fair game. If you solve that, you get y is equal to 8. So the price for y to make this a fair game, if the payment per game is $7, is $8. Okay, guys, thank you for listening to that. We're going on to the binomial distribution next.